Integration by parts, the trigonometric integrals, which we have the identity, and then using that identity to solve the process inside the integral. And then we have the trigonometric substitution, which we have now. We can substitute, for example, for this one here, we can substitute the x with the secant. And how do we substitute is based on these two identities, sine squared plus cos squared equal 1, and tangent squared plus 1 equals secant squared. Okay? So it depends on the structure in the integration equation, we can substitute with the trigonometric functions. Okay? And then after that, we are going to work on those integrals until we get the result. And then don't forget that after we get the result, we need to turn back this into the x, because the question is obviously asking in variable x, so we need to go back to this x form. How to do that? We are getting this from our substitutions. For example, here we have the x equal 3 secant theta, which means we are having the secant theta x over 3, and then we can get the idea for this triangle, and then based on what we have in the result, we can relate these two, and we can have the final result in variable x. Okay. So basically, we substitute x with trigonometric function. That is the way. Okay. And the rest, when we substitute, we can always take the derivative to change the dx as well, become the theta for this case, because we have a new variable theta. Well, actually, you can make this theta with your own variable. Okay, it can be theta a, b. It's up to you actually. But for me, I think because it's angle, I just say theta. Okay, it's easier. So that is the trigonometric sub. We have several cases. We change with the secant, we change with sine, and then we have also the third one. We substitute with the tangent when we have the x squared plus a constant like this one. And usually it's coming out like having a square root, something like that. And for obvious reason, you cannot do other technique, so you need to substitute with the trigonometric function. Okay. Sometimes it can be substitute, or it can be worked with other techniques. You can try that as well. If it can be solved by integration by part, you can also try that as well. So this will be the case, and then there are also cases that the function itself is not specifically showing that it can be substituted. So you need to tweak first, to rearrange the equation first, to get the idea that we can have this kind of structure. So from this x over square of this quadratic functions, we can complete the square, and then we can have the relations that, for obvious reason, we can substitute this x plus 1 with some u, and then from this u, we can substitute with the trigonometric function. In this case, we substitute with the sign, because it's 4 minus, so constant minus variable, we can have a sign. Okay? And then you can solve based on this, and convert back to u, and then from u to x. Okay? And then that's what we have in the final conclusion. Okay? Okay, so that is the first, the techniques for trigonometric substitutions. We are going to have some exercise later, but let me go through another techniques first. Okay, so after this is the partial fractions. Okay, so this is actually my original notes. Since last Saturday, I cannot do the live recording using my iPad, so only the audio that I can record. But I just showing you the original notes. If you see the video, I just uploaded this morning. So the partial fractions is basically a technique that separating a small fraction from big fraction. So it is especially in the integrals, it is really useful if we can slice and cut the integral into piece by piece. Okay? So for example, if we have this, we can separate by taking this, becoming these two small fractions. And how do we do that? Is basically we are taking, if it can be factorized, for example, this one, x squared plus x minus 2, we can factor easily, and we know that this is a linear factor, then the top of the equation will be just a constant, okay? So the variation within the partial fractions is related to how the denominator will behave. So if you have a linear, then it will be easy, it will be just a constant on the top. So if we have another case, if we have a polynomial that is greater, the degree is greater than the denominator, we can rearrange by taking some division. We can rearrange the structure, become this, okay? Yeah, become this, and then we can integrate easily. So sometimes we can have a linear and also the other components that we call the irreducible factors, or factors that we cannot reduce anymore. Okay? Usually that is when the discriminant is negative. Okay? For example, this case here. Let me take this. Okay, so the first case is we have distinct factors. So all factors is 1, 1, 1. Okay, so for example, this one here, if we can factorize, become this 3. So we only have 3 factors and they are different factors. Okay, no multiplicity. Okay. So easy is still a constant linear factor. Okay, and then try to solve this, and I hope you can solve this first to partially separate the fraction. Okay. And the case 2 is we call the repeated linear factor. So we have a multiplicity. Okay. So for example, we have here the example x squared and then x minus 1 and then cube. So we have repeated factors. So when this happens, actually our arrangement, if we just take 2 components, it's become this. Okay. Every for example, if we have denominator that is squared, the top equation will be linear. If we have a cube, this will be quadratic. Okay? So we need to make this separations more simplified. So we can take this. So this is let me tell you, this is easy as long as you can identify how to write it. Okay? So first, look at this, x squared, x minus 1 cubed. So we have 1, 2, 3, 4, 5. So we have 5, at least 5 components, right? So we are expecting to write 5 fractions, okay? Because of this multiplicity. The first is write x for this one, and then x squared. And the top will be this constant a, b. Okay? The second one, or the third one, we start from the x minus 1. So we have x minus 1, x minus 1 squared, and x minus 1 cubed. Okay? Now if you combine this, for sure it will bring back to the original equation. Okay? So I think it's the structure is, if you see the pattern and you know how to write, this is the linear repeated factors. Okay? And then after that we can find what is A, B, C, D, and E. Okay? So this is actually the same thing as this one. Okay? But we want to make sure that we separate all the terms. Okay? So that's why it's pretty easy if you are having an integration. So if you split this with this 5 fractions, and then you imagine you integrate this one by one. It's much more easier rather than if you integrate this whole equation. Okay? So if you put, or if you cut the fractions and make it smaller and smaller and smaller, each fraction is easier to be integrated, right? So that's the idea of the partial fraction. Okay? To cut the big fraction of the integral, and then each small fractions can be integrated easily. Okay, that's the goal. Okay, but there are some variation. Okay, so let's say this is by default is the standard in the partial fractions, but there are some factors that still we cannot really reduce. And usually that is in quadratic form. We say this is the irreducible factors or irreducible quadratics. So when that's happened, for example, this x squared plus 1, we cannot really factor anymore. Because that is actually having an imaginary number or complex number, right? So how do we deal with this? So we keep that as a whole. So we keep that as x squared plus 1. What is the implication of that? At the top of the equation, we need to write dx plus c, or the linear equation. We don't write a constant anymore, but now we write a linear equation. Same with this, x squared plus 4. That is something that is not factorizable. And if you know this quadratic equation, you remember we call this b squared minus 4ac. This is, we call it discriminant. Whenever this less than 0, then this might happen. Okay? The complex number. So that's how we get this irreducible factors. When this, why I'm writing determinant should be discriminant. So discriminant should be less than 0. And how to deal with this x squared plus 1 when you have the integration? We need to remember that whenever we have x squared plus 1, for example, we have this integration of 1 over 1 plus x squared, like I'm preparing here. So let me put this all here, because I'm not sure why my screen is, every screen I get like crop on the left, so I need to shift all to the right side. So whenever we have 1 over 1 plus x squared, we can try the tangent inverse. Okay, this is also some patterns that you need to be aware of. Okay? So sometimes when the irreducible factors appear, maybe you need to try the tangent inverse as your solution. Okay? But how if we have like tangent inverse, for example, x over 2, if we derive this, we have this, right? So if we have integration of 1 over x squared plus 4, then we can take the relation from the derivative. Okay, so we look at the derivative. So 1 over 1 plus x squared over 4, and then we need to multiply with the chain rule, right? Chain rule from the x over 2, which is half. So we have, and then we simplify, multiply with 4 over 4. We have 4 plus x squared, multiplied by half, it's 2 over x squared plus 4. So if we can integrate this, it will turn on this, right? So if we integrate this, we need to multiply with half. Okay? So half tangent inverse x over 2. Okay? Okay, so anyway, that is how we confirm, and we can have these relations based on what we have in the relation on the derivative and the integral for the tangent inverse. So we can have this 1 over a tangent inverse x over a. And again, this is not something that you need to remember or need to memorize. This is something that you need to understand that this is different. If you just memorize this, then you don't know how to use it, it's become not really useful, right? So how do we know that it is useful? From here, okay? From this relations, derivative and integrations. Okay? So whenever you have something that is related to the tangent inverse, you can try first to derive, because derivative sometimes makes more, it's more easier than the integration. So my suggestion is every time you have like after you take the integrations, and if it's still simple enough, try to derive again. If it is going back to the original one, then that will be your solution. Okay? So this is the relations between tangent inverse and the 1 over x squared plus a squared. Okay. And today we are going to have a calculus for 3 hours. Because last week you have TA class for 2 hours, so now we have 3-hour class. But I think we can finish early. Okay? Not exactly 3 hours. Maybe finish maybe 30 minutes earlier. Okay. So next week we have final exam, right, on Thursday. Just to make sure that you remember. Okay, let me check. What should we put down here, down there? Okay, partial fractions finished. So I think let's go for a little exercise, or maybe just to make sure that we have another variation for this part is if we have the irreducible factors, what we can do is if it is repeated, then we can treat like the linear repeated factors. For example, we have x and then x squared plus 1 and then squared, which means that this have another multiplicity. But the multiplicity now in the irreducible factors. What we deal with this is we take, for example, x, okay, just a constant, and we have x squared plus 1 and then x squared plus 1 squared. And how about the top? The top will be the linear equation. Okay? So I hope you get how to identify all the components. Okay? You have linear factors or you have irreducible factors. Okay? Or you have different factors. Just you can think like that is just like a regular factorization. Okay? So that is some of the possibility. Okay? And the rest is we need to solve this and finding the constant. So all the constants here. So for example, this one here, I've already done this for you. So we take, for example, a, and this will be x squared plus 1 squared. And for this one, we have bx plus c multiplied with x and x squared plus 1. And the rest will be dx plus e multiplied by x. And then we are going to simplify and then group all the variable. The variable will be the x4, x cubed, x squared, and x, and a constant. And then how to solve is basically just equaling the right side and the left side. The left side is the top equation here. Okay. So a constant is 1, which means 1 is a, and then x will be this c plus e, and then the x squared will be 2. 2 equal to 2a plus b plus d, and negative 1 is c. So we have already negative 1, and a is 1. And then the rest will be 0. So a plus b is 0, right? Because there is no x to the power of 4. And then we solve and finding the other component. So we have a equal 1, b equal negative 1, c equal negative 1, d equal 1, and e equals 0. So we get everything and we put back into the equations. Okay? We put back into the equation and then we do the integration separately. Okay? And after we integrate, we give in one full answer. Okay? Sometimes you have the x squared plus 1, sometimes you have the tangent inverse, or for this case, maybe just regular substitutions will be sufficient. Okay. So that's the thing. Last one. Okay. I think we can go for some exercise. Do you want this one? I think to maybe this one. Okay. Any idea which one should we discuss? I think you can focus on the right. This 23 to 36. Any idea which one? Any idea? Which one? I think maybe. Do you guys have a idea which one? Twenty-six. Okay, nice. Okay, let's try number 26. So let me write here number 26. Zero to 0.3 x over 25x squared. Okay, perhaps the power of 3 over 2 is a little bit troublesome, right? So maybe we can write this as square root and then cube, right? And now we have a constant, and this is supposed to be variable, but the variable itself is usually we have the same 9, right? So we know, like, if this is 9, then maybe it will be 3 sine or 3 cosine, right? But we have 25, so maybe it's not exactly like 3 sine, but the constant may be a fraction. Maybe a fraction. So what is the fraction? That when we multiply here, it will remove this 25. So we are expecting something over 25. And of course, we want to have the same as 9, like with this one. So 9, right? 9, so we need to multiply with what? 9 over 25. Which means 3 over 5. Do you get it? So let me write here. So we're expecting to be like this, right? So we want to remove 25. So we want to remove 25. So we want to multiply with this, right? We want to look at with 9 over 25. So this will be the constant that we are going to substitute. Okay. So 9 over 25 or 3 over 5. And we can choose sine or cosine, right? So we can let the x will be, for example, maybe sine, okay? Because if we derive, it's still positive, right? So let's say this. So when we derive, this will be 3 over 5 cosine theta d theta. That is for the dx. So let's change everything. So let's change. So this will be 3 over 5 sine theta. Now this will be 9 minus, this will be 25 multiplied with 9, 25 sine squared theta, like that. This will be cancelled. And then don't forget that we have dx, which is 3 over 5. So this will be here, 3 over 5 cosine theta, and then d theta. Next thing is we try to solve first. Okay, we try to simplify. So 9 minus 9 sine squared will be 3 cosine theta, and then cube, right? Cube. So we have, well, I don't have any space here. Let me just erase this. Okay, wait for a moment. Let me make this. Let me arrange this. Maybe here. And this will be here. Maybe make it smaller a little bit. Okay, now we have, the endpoints. Since we have changed the endpoint, so when x is 0, x is 3 over 5 sine theta. So when it's 0, then theta will be 0, right? So when x is 3 over 10, right? 3 over 10 or 0.3. So this will be wow. Why? Okay. Okay. Yeah, I don't know why it's like sometimes it's showing the full screen, sometimes it's only like cropping the left side. I don't know why. So sine theta is 5 over 3, which is half, right? So theta is pi over 6, okay? Okay, with the assumption that the theta will be only on the acute angle, so this will be 0 and pi over 6. Okay, we solve now. So 9 over 25, I'll write that. This will be 0, pi over 6. This will be 3 cosine theta cube. And then this will be sine theta, cosine theta, and then d theta. Okay, I think we can cancel this, so it will be squared. So 9 over 25. Oh, we have 3. Oh, sorry, should be right. 27, I think the better. So 27 cancel with 9, right? So it's 3. So we have 1 over 75. Okay. And then we have 0 pi over 6 sine theta over cosine squared theta d theta. Now what should we do now? Give up. Now what should we do now? What method should we now use? Yeah, I heard someone say the correct one, but I think they just whispering. Yeah, substitution. Yes, substitution. Which one you need to do substitute? Which one? Yeah, cosine, because we can cancel the sign and it will be 1 over u squared. Okay? So we can substitute. So let u is cosine theta. So du will be negative sine theta d theta. And since we are taking another substitution, we change again these endpoints. So when theta is 0, u is 1. When theta is pi over 6, u is cosine pi over 6. What is cosine pi over 6? Yeah. Yeah, Franco. You need to know. Okay. Yeah. Square 3 over 2. Okay. Okay. So we can exchange this, and since it's negative, so it's become negative here, and this will be 1 to half square root of 3. And the sign will be cancelled. This will be u. So I will change all into u. So integrate, we get, this will be negative 1 over u, right? Plug in 1, plug in this square of over 3 over 2. Okay. Or we can multiply the negatives and we write 2 over square root of 3 minus 1. Okay, and then I will just stop and then that's the answer. But since it is a definite integral and we compute directly, we don't need to worry on going back to the Okay. Any questions? Any questions? Anyone lost here? From here. This du. So d theta is 1 over negative sine. And sine is cancelled. Cosine becomes here. Okay, and then d. Okay. Maybe one more exercise, but from the partial fractions, okay? Partial fractions. Okay, let's try. I hope you don't get dizzy looking at this. Oh, by the way, I put in the Moodle, so if you want to check, I put like separately as a note. Also the previous final exam, I also put last year finals, if you want to check what kind of question I have. But every year, I tend to have like different questions. Yeah. So this all is one is using the partial fractions. So the idea, partial fractions, it's not about the integration itself, but how to separate these big fractions becomes like small fractions. And that's the idea. So if you feel maybe not confident on the integration, just cover it first and then try to separate first, okay? And then at the end you can put the integration. Okay? That's one way. Sometimes when you try to solve and you looking at this integration, you feel perhaps anxiety and then, I don't get it, and I cannot find a way. But you can start from here, okay, and then separate the integrations. Okay. Okay, which number? Which number though? Maybe focus on the left first. The right is a little bit difficult. Maybe on the left first. This is the usual partial fractions. Which one? Any idea? What number? Which one do you want? Yeah, any idea which one? My favorite number is 19? 19? Nobody. 19, here, this one, right? 12? 12?
They say it's easy. They say it's easy.
Yeah, it's easy.
Which one is the hardest one?
The hardest one, I think I consider the hardest one is around here and around there. So maybe focus here first. 18? Agree? 18? Okay, let's try. Or do you want to try also? You can. Okay, let's try. Yes? 22. Which one is 22? Okay, it's power of 4. Okay. So, my suggestion to solve partial fractions, you need to have like skills on polynomials. For example, to find the factors using polynomials, there are several methods. The long division, the syntactic division, and I prefer the syntactic division. It's easier to find the roots, because the idea here is we need to find how can we factor this. But I think it's easy, right? Easy to factor. There's no need for polynomials. It's the quadratic. So let me write this. Let me put this above here. And let me write down here. So number 22. So 3x squared plus 12x. Or maybe let me write just the fraction first. Over x with power of 4 minus 8x squared plus 16. So first is we focus on the denominator, and can we do something about this? So if you think that this is, so we have 4, we have squared. So perhaps if we exchange the x squared with one variable, maybe it will help you to see. So let's say we have a is equal x squared. So let's say this will be a squared minus 8a plus 16. So we can have a minus 4, right? Squared. Is it? Right? Yeah. So we can have our factors 3x squared plus 12x. Okay, we have that, which means that this will be x squared minus 4 is, we can have x minus 2, x plus 2 squared, right? right? So we have x minus 2 squared and x plus 2 squared. So we can have four components. So 1, 2, 3, 4. So first one is x minus 2, the second one is x minus 2 squared, and then the last one will be, or the third one is x plus 2, and all is linear, right? All is linear factors. So plus, 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 A, B, C, D. Okay, now we start to solve the linear equations. So, so A multiply with x minus 2 and plus B and then plus C x minus 2 squared and x plus 2 and plus D x minus 2 squared. It should be equal to, okay, we have a break for a while. Okay. Okay, let's go try to solve this. Okay, my first question. If you have this, what will you do? What will you do? One way, you can multiply and then group all the variables. Another way, see this x minus 2, x plus 2, x plus 2, x minus 2, blah, 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 right? So we can think and let x be equal to something that's easy to compute. For example, if I take x equal to, this will be 0, this will be 0, this will be 0. So I will get this then. If I take x equal to, and we can take x equal to for this one as well. So we get the complete equation. Okay. So let's try that one. Okay. So we can let x equal to some constant that's easy to compute. Okay. So we can compute a, b, c. Okay. So let x equal to. So this will be 0. This will be 4 squared, so 16b on the left, 0, 0, and then the right side will be 2 squared for 12, 12 plus 24, 36 minus 20 is 16. So b is 1, so at least we get one component. Okay? And then try another x. So try x equal negative 2. 0, 0, 0, and we get b, right? So this is actually one idea, right? So rather than multiply everything, you can try this one. You can set some x that's easy to copy. So let x in negative 2. It will give you, this is 16d equal 4, 3, 12. 12 minus 24, so negative 12, negative 20, so negative 32. So D is negative 2. So we have B and D. And what else? The number that we can choose. We can take x equals 0 or 1. I think still easy to compute because it's only -2 and 2, right? So we can take 0. So -2, and then we have 2 squared, 4, 4 minus 2, -8, a. So we set x equals 0. So x equals 0. So this will be -8a. This will be 2 squared 4, so 4b. But b is 1, so plus 4. And then c will be 4 to 8c, so plus 8c. And then d is -2. So -2 squared is 4, so 4d. So 4d is 4 by 2, so -8. So take 0, this will be -20. So we can have so -4 move to the right, plus 4, so -16. And this will be -8a plus 8c. Divide by 8, we have this equation. So let me just make a line there. Another number that we can think is x equal 1. Maybe it's still easy to compute, right? So plug in 1, so -1, and then 3 squared, 9, so -9a. And then 3 squared is 9b, b is 1, so plus 9. And then this will be -1 squared is 1, 3c, so plus 3c. And then we have -1 squared is d, so it's -2. This equal to 3 plus 12, 15 minus 20 is -5. So 9 minus 2 is 7, 7 move to the right, it's -12. This will be what? -9a plus 3c, divide by 3. And then we solve with the left one. This is -a plus c. Let me subtract this. This is -2a. And careful on subtraction and addition. Careful on the signs. So a is 1. And then -1 plus c is 2. So c will be 3. Why? C is 3, right? Why? Oh! Why I'm writing +2? Okay. So C will be -1. Okay. And we're still not finished yet. So we need to go back to the integration. So we get so the integration of the 3x squared plus 12x minus 20 over x with power of 4 minus 8x squared plus 16 dx is equal. So first is a is 1, right? So a is 1. 1 over x minus, I will separately integrate like this, okay? And then plus b is 1 over x minus 2 squared dx. And plus or minus now, because of -1, this will be 1 over x plus 2 dx. And d is -2, so minus 2 let me copy this. Or maybe let me just write here, taking all precise okay. 1 over x minus 2 is, we can write ln x minus 2, right? And we can use substitution for this one, 1 over x minus 2 squared. This will be negative 1 over x, right? So 1 over x minus 2. This is the same. And then this will be also the same. Negative, negative, positive. So 2 over x plus 2 plus c. If you want to simplify the log of the ln, you can do as well, but I will just stop here. I'm lazy now. I will just stop here. If you do this in exam, it's correct. No need to simplify to the end. Just the important point is the partial fractions and the integration. Okay? Okay, any question? Well, this computations, like taking x equals some numbers, mostly works, but sometimes it won't work. When it does happen, you need to expand the equation and just solve it. And of course, I will prepare like a good question. I mean, good is like when you read the question and then you feel that you write a long solution. That's not a good question. A good question is sometimes you just need only to provide like a small part of the answers, and that's a good question. I'm trying to do that so we can have to optimize your time. Right? So that's my suggestion. Every time you feel you are going nowhere, my suggestion, skip that question and work with another one. Yeah, maybe that will help you. Okay. I think I need to go to the next section. So one more section for this semester, which is the improper integral. So next week, I will have, so before the finals, so finals is the Thursday, right? So the Tuesday, I'm going to prepare a review class. So we'll be having an exercise, and I think the last hour will be the TA also. So I will prepare the exercise, TA also prepare an exercise. And hopefully we cover everything. Okay, next is, okay, so there are still some exercise here that you can, I put the exercise itself like separately. You can check the Moodle. This one, that's like crazy integration. So we move now to here. Okay, so this is, we call the improper integral. So what we've done so far, generally we call that as an integral or the proper one, which means that there are nothing wrong in the equation itself, nothing wrong in the functions. And for this one, if we look at, for example here, we have 1 over x squared. And then we would like to know, like, if we want to compute the area under this curve, okay? So between the x-axis and the curve. Like, of course, if we have the integration, if we have the endpoints, of course we can. Okay? If we state which one is the endpoint. Like, for example, if we have like this 1 to 2, we have like 1/2, okay, based on the function itself. And then if we have like 1 to 3, we can have the area is around 2/3, and so on and so forth. And if we increase the endpoints, like from 1 to closer to infinity, getting larger and larger, well, the area is actually from 1. Okay, so let me give you the relations. So we start with this. So let's say we have 1 to t of the 1/x² dx. And of course, 1/x², we can get integrated easily and become negative 1/x, okay, from 1 to t. So this will be 1 minus 1/t. So we are taking this 1/t to every area that is going to be calculated. For example, we take it for this 2. So 1 minus half is half. 1 minus 1/3 is 2/3. 1 minus, now it's 5. It's 4/5. Now if we can imagine that this t getting larger and larger. So if we take the limit of t getting larger of the area, this means that we are going to take all the limit property in the early classes and then use that in our integrations. So we have this is 1. So we say that the area of the infinite region will be equal to 1. So there are some cases that when we try to compute, when we increase the interval larger and larger, the area itself is finite. So it's finite is 1. But it's actually the area is getting larger. Okay. So there are some conditions that makes that happen. So we call that the improper integral. So it's improper because it's actually the rough idea. Okay, the rough idea is actually we tend to integrate this. This can be any constant. But we want to integrate with the endpoint is getting larger or closer to infinity. But of course, if we have this directly in our equations, we cannot simply integrate. What we can do, however, we can take this like equal to t, and we can compute this first. And then we can take the limit of that t, and then we can have it. Okay. So that's how we process. Okay. So for example here, in this case, the f/x is 1/x². We are going to take this into this this t. So we can write here and then, okay, and this is equal 1. With the same process as we did in the first place. So this is improper integral, the first type, okay, which we have the endpoint having infinity. Okay. Or we call this an infinite interval. If the limit exists, we call that is the convergent. If limit doesn't exist, we call divergent. Okay. Let me write here. Maybe make it this smaller. And let me write here. Limit exists, we call converge or convergent. If limit doesn't exist, this will be divergent. Okay, let me write a conclusion about this, okay, in the definition. So here is the definition that we can take a look. Okay. So it can be from negative infinity to some number b, or from a to infinity. Okay. But the idea is every endpoint that has infinite interval, we can substitute for t to process our integral. And later, we take the limit to process the t. Okay. Well, actually, it can be any variable you want, but usually, technically, the textbook using t. But you can use any variable. Okay. And if the limit exists, we call it divergent. So the improper integrals, the two integrals, is called convergent if the limit exists, or we call that divergent if limit doesn't exist. And of course, if we take the interval from negative infinity to infinity, we can separate. Okay? We can separate and make sure that we know the number in between. Well, because it can be any number. We can choose number that easily to be computed. Okay? Number that easy to be computed. It can be 1, it can be 0, usually. So we can separate and then we can integrate separately. Okay? Okay. Okay, so our goal by taking this improper integral is to define whether some integrations can be converged or diverged. And there will be some method as well, but technically only one method. So, from the previous example, 1 over x squared, if we take integration from 1 to infinity, we have that 1 over x squared here exists, right? Or we say it's convergent. Okay. But later, I will show you that if we have 1 over x, although it's quite similar to 1 over x squared, 1 over x will be diverged, okay, based on the integration itself. Okay. And then we take the limit doesn't exist. So if we look at here, so if we take a look here, so just to make sure that we are able to compute the 1 over x, let me write here that the 1 over x, if we take integral from 1 to infinity for 1 over x dx. So we take limit. So 1 over x, we take integration, it becomes ln, right? From 1 to t. So this will be ln t minus ln 1 or 0, right? So ln t, so ln infinity, it will be infinity, right? Or we can write this ln t, limit doesn't exist. So we say that integration from 1 to infinity for 1 over x dx is divergent. Now, as you can see from the figure, from the picture, the 1 over x squared, we have the finite area, and you will see the comparison, okay, the gap between the x-axis and the curve. If you compare with this, it still has some area. Although it's small, but it's not as much smaller than this one. Okay. If we try to increase the x, it will be like really, really thin gap between the curve and the x-axis. But here is still much more observable. We can still see some gap from this curve and x-axis, which means that the area will be infinite. Okay. And to make sure that our observation correct, we can check and using limit approach for the integral. We take the improper integral with some techniques here, and we get that this is going to be divergent. So 1 over x squared from 1 to infinity is converged, but 1 over x is diverged. Now from these two functions, we can make some general idea for 1 over x with power of something. Okay? So let's say, usually we say that power of p. So let me write here that suppose that we have 1 over x with power of p dx from 1 to infinity. Now we take the limit and exchange the infinity. And then let's say the p is a number, okay, a number, positive number p. Okay. So this could be written as, and if we take integration with this will be x. This is x minus p, right? If we take to the top. So this would be minus p plus 1, or 1 minus p. This is 1 minus p. Okay, which we integrate. We plus 1, right? This is going to be integrated from 1 to t. 1 over 1 minus p is a constant, so we can factor that out. This will be x minus p, so t 1 minus p, so t 1 minus p, and then plug in 1, it's just 1, right? Because 1 minus p is a constant, so that will be. And then still we can write this let me put this maybe over here. And then this will be, we can write this as 1 over, we flip the p minus 1 and then minus 1. Just to make sure that what we have here will be 0. Okay. So it could be 0 if p is greater than 1. So we have two choices, at least two choices here. So p can be greater 1 or p less equal 1. When p greater 1, p minus 1 is greater than 0, which means that this will be equal to 1 over p minus 1, or this will be converged. Let me put this a little bit to the right. And when we have p less equal 1, or to be written as this, then if we write t 1 minus p, so as t increase, t minus p also increase, right? So that's why this become diverges. So my conclusion here that if we have 1 to infinity for 1 over x power of p dx, we have two conclusions from here will be converged if p is greater than 1. This will be divergent if p less equal 1. Well, ln infinity is infinity, right? Doesn't exist. We consider that infinity will be limit not exist, right? Not a finite value. Okay. Or maybe if you want to write infinities, okay. If you want to write here, this will be equal to infinity. It's okay. 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 Okay, any question? Sounds like we're going to sleep. Okay, but the idea is a proper integral. The goal usually, we need to make sure that we can provide whether the integration will be converged or diverged. Okay? So the way we take the integration is just like usual integration, but the difference is we are going to use limit and change the end point. However, there are another types for a proper integral, the second type. So there are two types. The first one that we've done here, the interval that is having infinity. The second type, if we have discontinuity. Okay, so if we have discontinuous functions, we can try to make out the integration if we know where the discontinuity happens. Okay. For example, here I will have the definition, but let me just write and just give you an idea first what is going on here. So suppose that we have this two curve that, let's say at this A we have the asymptote, this C also asymptote. So this is where the discontinuity happens. Let's say that is our discontinuity. Okay. So if we know where, like for example, this is when x equals A, this is when x equals C. Now we can try to find using limit, the same limit that we have discussed. So we can take, for example, here, we can take limit from the right. So we can take limit as x approaching A from the right. And using the same integration, and take the limit. And basically that is what we are going to solve. And usually for this one here, we can take from the left, we can take from the right. Okay. Depends on the also depends on the question. Okay. So that's how we define this type, the second type. So let's say we have discontinuity. For example, the first one, if a function is continuous at some certain point, let's say from A to B, and then at B it starts to discontinue. So that's why we have this bracket here, which we stated that we're not including B. Okay? And then discontinue happen at B. Okay, so we take the limit from the left. So this is actually like this. Let me write here. Let's say this is discontinuity. This is B. This is A. So we take from the left and approaching that discontinuity. Okay. The second one, we have discontinuity at A. So we are going to approach from the right. Okay. From right of A. And of course, both it will have a value if they both exist, okay, as a finite number, and we call the improper integral will be convergent if the limit exists, okay? And it's divergent if limit doesn't exist or infinity. And of course, if we have the discontinuity in between, okay? So the discontinuity is in the middle, so we can separate, and we know that the C is between A and B, so we can separate the integration, and both integration we take the limit, okay? Limit from the left and limit from the right, okay? To the number C, to the x equals C. So this is precisely the, let's say this is C, this is A, this is B. Let's say we have that. So we are going to approach from the left and approach from the right. So we can take limit here as T to C from the left, and this is limit T from C from the right, okay? Okay, so that is the improper integral type 1 and type 2. Since the class will be 3 hours, do you want to have like early finish? Or do you want to take a break for 5 to 10 minutes and then we get back and then we move until usually when you will leave the class? For 20 or 30? For 20, right? So maybe we can finish 3 maybe 3:45. I'm asking, like, if you want that, maybe now we can have a break, 10 minutes, and then, okay? Is that okay? Okay, let's continue for a while, for around 30 minutes. or 35 minutes, okay? And then we can have early classes. So, as an example, how to work out the type 2. What you need to be careful is the domain of the functions. Okay? So for example, if we have an integration, so example, so let's say we have 2 to 5 of 1 over square root of x minus 2 and then the x. So we have this, and look at the endpoint. So for obvious reasons, this will be restricting our domain. Right? X should not be equal to 2 at least. Okay. So, and also the square root also restricting our domain as well. So the endpoint has this number 2, which means that we need to slowly taking this 2 and substitute to some variable, and then let the 2 equal to some variable, and then limit it to that we can approach this using limit. Okay. So we can take this and write the limit. Okay. And then basically, what is the integration of 1 over square root of x minus 2? How to integrate this? I think this is also one of my suggestions to make it the process faster. So if you imagine the square root of x, okay? If we take derivative, this will be 1 over 2 square root of x, right? So we are going to see the square root of x again, which means that if we want to reverse the process from here to here, which is the integration, we can do this, and then we have to have the 2, right? So we need to multiply 2. Do you get my idea? So I can get this directly, right? 2 square root of x minus 2 and then d5. Do you get it? Okay. Okay, so we can do that as well. And then we can plug in the information. So this will be 2 square root of 3 minus square root of t minus 2, which is, if we plug in, this will be 0, so this will be equal to 2 square root of 3, which is converged, so we can know that this will be convergent. So what is the official way to start this? Is just using substitution. Using the substitution. If you want to write like in the notes. But if you want to make it fast, just remember this. If not, then use substitutions, and this is x minus 2 is u, and then this will be square root of u, and then it's half minus half plus 1 is become half, right? And then we need to take that as well for the 2 in the front. Okay. Okay, one more section within this improper integrals, and then the theory are done. So the left is only practice and exercise. So whenever you see an integrations now, since you have now improper integral, be careful on this. Sometimes it's not like this is quite obvious, right? This x minus 2, this is 2. But sometimes maybe you have the endpoints, but maybe the one that makes this continuity is in between. So that's also, you need to be careful. Okay? So always see the domain and check whether the domain is on the interval of the integration or not. Okay? If it's in the interval, then you need to make separation. And then integrate and take limit. Okay? Okay. So another test that we can have, we call the comparison. It's similar to what we have in the first limit. We have we call the squeeze theorem, right? But this is quite, I think, not really complicated. It's quite direct. So we call this is a comparison theorem. So suppose that f and g are continuous functions, and f is greater than g, and both are positive functions. It's greater than 0. For x is greater than some constant a. So if f of x converge, of course, g, since g is less, g also converge. Okay, the first one, I think, no big deal, right? But the second one, if g diverge, okay, then f should be diverged. Now the problem, if we know f is diverged, how about the g? So f is diverged. G is not necessarily diverged, right? It can be converged. But if you think carefully, think carefully. This is quite used on the logic thinking. So if f is finite, right, this is the value, and since g is below is f, so g should be converged, right? Okay, easy. Okay? The second one, f is greater than g. If g diverge, then f that is here should be diverged. Okay, but if f is diverged, g is not sure. Okay? It's unsure. Okay. And basically, how do we use it is technically similar to the comparison that we have before. So if we take, for example, if we take 1 to infinity, let's say 1 plus e if the question is asking only converge or diverge, then we don't really care what will be the computations. We only care whether the function or the integrations will be converged or diverged. So what we need is how to compare this with another function. So we need to find another functions that easily we can recognize whether it is converged or diverged. Okay? And then to prove whether this will be converged or diverged, we are going to make like f is greater than g. Okay? So that's our theorem. So we need to state the theorem and make sure that this is satisfy the theorem, and we can have as our answers. So if we have this, we know that the e is always positive, right? So we can write 1 plus e with power of negative x. This always greater than this. Okay? Because this is always positive, so this will be at least greater than 1. So it's supposed to be true, right? It's supposed to be true. But this is already greater than this. And then we know that this will be, if we take the improper integral, we can just directly state that this is diverged. you don't need to write the process again. Just state that this is already stated by the 1 over x to the power of p. Okay? This is 1 over x, and this will be diverged. So since this is diverged, okay, so this will be diverged, and this is greater than this. So this will be also same. Also diverges by comparison theorem. Okay? So sometimes for a question that doesn't really need to process the computations, doesn't really need to know like the value if you have the integration, then you can try to use this method, okay? Especially if you are looking at the integration and it's not really easy to follow or maybe to solve. And then the question is only asking whether it's converged or diverged. So you can just go directly to the comparison here. Okay, there are some practices as well I prepared here. And also here, this is precisely asking the comparison theorem. Maybe we try one question from here, and then I forgot to mention one notes, but I think that will be for the last one. So maybe one question from here. Which one? This is using comparison, okay, comparison theorem. Which one do you think we should try? Which one? 59. Okay, this is quite good. So 1 over x minus ln x. But I think it's quite, if you think carefully, so 1 over, let me write, this is 59. So 1 over x minus ln x. I think we can just use 1 over x, right? Okay, 1 over x. So we can, let me just write 1 over x first. If x equal 1, so it doesn't have the endpoint. So let's say it starts from 2. So maybe if we take some numbers in between, it's always, remember ln 2, 3, 4 is always in decimals, right? 0 point something, right? So if we have, for example, 2, so 2 minus 0 point something, it will be 1 point something, alright? So what does it mean? It means that this will be greater, right? Okay? So, since this is greater, the limit or the integration with this is diverged, right? And then the question is to also diverges by comparison theorem. Okay. Okay, you can try the other one. I will put the notes for the exercise for improper integral later. I will go back. I forgot to mention some of the special integration by parts. Let me write. Okay, this one. I forgot to mention the secant x, and the secant cube. And let me just solve this, okay, for you. So first is the secant x dx. Okay. So how do we find the solution for the secant? There are several ways, but I think the best way to approach the secant, if you look at the derivative of the secant, we can have a secant x, tangent x, right? If we have a tangent, we have a secant squared, right? So based on these two, we need to multiply, like a rationalization, to multiply something with the secant that we can relate to these two. Okay. So long story short, we'll just make it very quickly. The secant x, I will multiply with secant x plus tangent x and secant x plus tangent x. Okay? I can do this, right? Because this is technically 1, right? This is technically 1. Okay? So I can just multiply with this. And what's happened when we do this is we are going to have a secant squared x, secant x tangent x, and then we have secant x tangent x as denominator. And then we can have some structure that is very good for substitution. Okay, if you look at what we have the relation between. Okay. So we have now secant squared x plus secant x tangent x. So if we let the u as secant x plus tangent x, so du will be secant x tangent x plus secant squared x dx. So dx will be 1 over secant x tangent x plus secant squared x and then du. So then this will be fit with our equation, in which this is going to be canceling the top equation, right? Okay. So we are going to have integration 1 over u, and then the whole thing we can just write, let me just write and this is technically the same thing. This will be du, this will be cancelling, right? So integration of 1 over u will be ln, and u is secant x plus tangent x, right? So this will be plus c. And now using this secant, we can now perform the integration to the secant cube x dx. Okay. So secant x done, secant squared become tangent, secant cube. So this is also considered like a little bit more advanced integration. So secant cube x. Any idea? Have you tried done this before? Anything? Any idea? Huh? Yeah, it's 3. Like it's like this question, like small question, right? So if this happened in your exam, and like this is a small integration. This is very hard. Yeah, but what? But this already has like cube, right? Yes?
Can we make it secant x and with 1 plus tangent?
Yeah, we can do that. But before that, let's just separate secant and secant squared. So we can separate this, okay? And then we can take this part become our integration by parts. Okay? Since we know that the derivative, so let's say d is the secant x and the integration will be secant squared x. So the derivative will be secant x tangent x. If you take integration, will be tangent x, right? With multiply positive and multiply with that. Technically, this is just a normal integration by parts. Okay. So this will be secant x tangent x minus integration of secant x tangent squared x dx. Okay, now what will happen? The tangent squared, I can rewrite tangent squared as a secant squared minus 1. So let me write secant x tangent x minus secant x and then secant squared x minus 1 dx. Okay. And then we solve this. Okay, write again this part. And then this will be secant cube x. Okay. And then minus secant x. And then the x. Okay. Now if you are not careful enough, and then you maybe not observing the left side, you will try to make some cycles here and it will not going to be finished. You will go loop, you are going into the loop and you will go into cycle here. But if you observe, and this is I think one suggestion, write the left side always, because you see that this, we can move to here, right? And we can divide by 2. Okay? So we can write, so technically this is going to be negative secant cube x dx and plus secant x dx, right? So I will going to write this as 2 secant cube x dx, and then this will be secant x tangent x, and then the integration of the secant x we have done here, right, which is the ln, and then plus ln secant x plus tangent x. So secant cube x dx is half secant x tangent x plus half ln secant x plus tangent x, and then plus constant. It's going. Okay. Okay, any questions? I hope you still remember how to do the integration by parts. Technically, this is u and u dphi. Okay. This is u dphi, u du, phi, dphi, phi. Right? U dphi, u du, dphi, phi. Okay. It's actually from here, right? Oh, not showing up. Okay, I think that will be for today. Is that okay? So the whole topics, we've done it. This Thursday, I will give some additional notes on the improper integrals. Okay. Actually, I'm preparing the one more topics, but I think maybe too much. It's on the chapter 8.